Bismillah ar-Rahman ar-Rahim. Today, inshallah, we're going to cover chapter 5. So let's begin. I personally actually hate this chapter so much because it's just implementing bunch of formulas. There is not much thought-provoking concepts in there, except for towards the end of the chapter. There are some interesting things there, but for the most part, it's just boring solving questions using some pre-given formulas or something of that sort. So let's start with the first title of the chapter. So the first title of the chapter is the joint probability mass function. This chapter actually is a generalization for the previous two chapters. So in chapter 3, we took probability mass functions. Now we have the word joint to denote that we are going to be dealing with more than one random variable at a time. Recall, in chapter 3, we had only one random variable at a time. We only set probability of capital X and then we found the probability. Now we're going to have more than one random variable at a time. Naturally, capital Y, capital Z. But for the most part, we're going to deal with two random variables at a time. There is a section where we deal with more than two, but for the majority of this chapter, you're going to be dealing with two. Okay? So the joint probability mass function of a discrete random of the discrete random variables capital X and capital Y is a function such that, and here are the conditions that need to be met, so we can say that this function is indeed a joint probability mass function. So the first one tells you basically that whichever value that come from this function should be strictly non-negative. Okay, so it could be 0, it could be greater than 0, but it should not be negative whatsoever. The second one tells you that the values that come out of this, if you sum all the possible combinations of X and Y of this probability, obviously in the domain of X and the domain of Y, you should get 1 at the end. And this looks very familiar to us because it basically is what you are thinking of. This just basically tells you that if you sum all the probabilities for all the possible outcomes you have inside of this probability mass function or distribution, you should get 1 at the end. It's just basic. The last one tells you for whichever combination for X and Y that you plug inside of this function, this should be equivalent to finding the probability of this said X and this said Y. Naturally, it's called probability mass function for a reason. It finds probabilities. So I'd be surprised if this was not there. So let's solve a question based on that. We have this table here where we have the X values or the outcomes for X in the first row, and we have the values for Y in the first column. And we have a set of questions. We're going to see them all, but let's solve this first question here. It's basic. It's like finding the coordinates on a Cartesian plane. It's extremely simple. So the probability of capital X equals 2, capital Y equals 3. You go to the table. Here is the outcome 2 for X, and here is the outcome 3 for Y. And where these two imaginary lines that you draw in your mind would intersect should be the probability that you are looking for, which is 0.1 in this case. Let's move on. Let's solve this question here. The question says fxy of 1 and 3. So this basically is like saying finding the probability of capital X equals 1 and capital Y equals 3. So let's go to the table. Here is X equals 1 and here is Y equals 3, where this line intersect is here, and this is going to be the probability that we are interested in. Second question, probability of X less than or equal 1 and capital Y equals 1. So just logical, just use intuition and logic. It should be extremely easy. So for X being less than or equal to, these are the two outcomes that we are interested in, and for Y equals 1 is this outcome. And where these two imaginary lines intersect, or three imaginary lines intersect, you're going to have these two probabilities, and you can basically sum them and find the probability that you are interested in at the end of the day. Or you can write it in this mathematical way if it makes it easier for you. Just very easy to get the grasp of. The next one, probability of capital X greater than or equal to and capital Y less than or equal to. You can do the same exact procedure, but this time I'm going to actually draw the line because it could be confusing following all of these outcomes, even though it's very simple. So for the first one, capital X greater than or equal to, it should include the outcome 2 and outcome 3. So let me draw these lines. And for capital Y less than or equal to should denote 2 and 1. And here where these lines intersect, this is the square that has the probabilities that I'm most interested in, and I'm going to sum them all to find the answer that I want at the end, which is 0.5. You can check it by yourself. I think, yeah, it should be right. Let's move to the last one. Probability of capital X equals 1 and Y going from 1 included up to 3 excluded. It's like saying Y going from 1 to 2. And also, actually, you can say that Y is less than or equal to. It's just simple. You can solve it by yourself. You don't even need me to explain this. Extremely easy. So it will include these two probabilities, and this is gonna be the answer at the end for it. Now let's talk about the joint probability density function. So for a function to be called the joint probability density function for variables capital X and Y, of course both of them are continuous, they need to have it needs to have these conditions met, or these let's say properties. So the first one is the non-negativity property. So all values coming from this said function are not going to be negative. And also, if you integrate over the whole region of X and the whole region of Y, you should get 1 at the end. Of course, integrating this said function. And bear in mind, I will bring your attention to it once again. This does not necessarily mean integrating down to minus infinity up to infinity. It just means to integrate from the lowest point you have in the range of X up to the highest point you have in the range of X, and here for the second integral down in the range of Y and up in the range of Y. And the last one tells you that the probabilities of these combinations of X and Y are merely the area under the curve of this bounded region that's denoted by X, or that is specified by X and Y. This is basically it. Let's solve a question now. So the question says determine the value of C such that the function, this is the joint probability density function, and here's the range of X, and here is the range of Y that we're going to be solving according to. So first of all, we have to find the value of C. It goes without saying, because this function is merely a function of X and Y, and C should be a constant, and we should find the value for this constant that would make this function a joint probability density function. I'm going to use the second property to solve this first requirement here. And the second property was saying that if you sum the whole, if you integrate this function over the whole range of X and the whole range of Y, you should get 1 at the end. So when we do that, theoretically X should go and Y should go, and the only thing that should remain with me is C as the only unknown, and I can solve for it. So when I do that, here I'm integrating over the whole region of X and the whole region of Y and equating it to 1. And here I'm going to find the answer eventually. So now I can actually find probabilities since I have the value for C. So whenever you see this question in the slides, the value for C is this one. So I don't need to, I don't need to write it all the way. So just remember that C equals 4 over 81. So let's solve the first question here, the actual first probability. So the question says probability of capital X less than 2 and capital Y less than 3. So basically we're going to integrate over the desired regions here. So X less than 2. So I'm going to from the lowest outcome in the domain of X up to 2. And here I'm going to go to the lowest outcome in the domain of Y up to 3. So this is basically the integral I'm going to be solving for. It's easier shown than explained. So integrating it basically will yield the answer that I'm looking for at the end. So second question, probability of X less than 2.5. So I have to integrate from the lowest value I have in X up to 2.5, right? No. Since we are talking about joint probability distribution functions, if you don't have the other variable in the expression, here in this case Y is not present in this expression, this is called the this is called the marginal expression. And these marginal expressions, if you don't have the other variable, you have to integrate over the whole region of the other variable. So in our case, we're going to integrate over the whole region of Y and over the region of X that we want to find. So our integral will look something like this. So see here, we're integrating over the whole region of Y since Y is not present in our expression, and we are dealing with joint probability density function. Here is the probability at the end. And the same goes for the last question. We have Y, but we don't have X. So we're going to integrate over the whole range of X, and we're going to integrate over the desired range of Y that we have, and this should yield the answer that we need at the end. Good. Now we're going to talk about a little bit more about the marginal. So the marginal has two cases, discrete and continuous, and for the variable capital X and capital Y, here are the formulas that you're going to use. There is a common theme here. You definitely want to remember them or find a way to memorize them so you can use them. So you can think of it in this way. So if you want to find the marginal of X, you're going to fix the X, and you're going to iterate over all the y's that you have. Just basically it. So if we want to use numbers in this case, let's say I want to find the marginal of x, equals 1 or something like this. So here we're going to have 1 fixed, and we're going to iterate over all the y's. So maybe our y goes from 1 to 4. So we're going to say, we'll find the expression of f of 1, 1, and 1, 2, and 1, 3, and 1, 4, and we're going to sum them all, and this is going to yield the marginal for f of x equals 1, or fx of 1. So basically, and the same idea goes for the y also, but instead of fixing the x here, we're going to fix the y. So you fix the one that you want to find, basically, and you iterate over the other one. Same goes for the continuous, same exact concept, just the only difference that we are dealing in the continuous domain, and in the continuous domain, we don't sum, we integrate. So if we want to find the marginal of x, we're going to integrate in terms of y, and if we want to find the marginal of y, we fix y and we integrate over x. That's as easy as it goes. Now let's solve a question in the discrete case first, then we're going to go into the continuous one. So here are the formulas that we're going to use, and here are the questions. So the first question says, find fx of 2, or the marginal of x equals 2. So you can use the formula, or basically you can look at this table, but bear in mind, this table is very nice. And not all tables that you have in the book are this nice. So in this table, you basically know that you can just go to outcome 2 in the table for x, and you sum all of these values, and you're going to end up with the marginal. But some tables are not as nice, so you might want to know how to write the mathematical expression for it, or write it in a mathematical way. So this is going to be the way that you write it. So here we fixed x, and we iterated over y. So here you can easily see it, and basically find the answer at the end. And if you sum all of these values here for x equals 2 here, you're gonna find the exact same answer. So let's move to the next one. The marginal of y equals 1. So this is y equals 1. You can sum all of these values you have in this row, or you can use the formula and you can fix y and iterate over the values of x. And you're going to end up with this answer at the end, hopefully. The next one, I think you can solve these by yourself if you want. If you want to pause the video and solve them, you can absolutely do it, because I'm going to show the answers in 3, 2, 1. So it's basically the same idea, same concept. So here for fx3, you can add these values here, or you can find these probabilities individually. It's going to be the same as these, but just writing them in a mathematical expression would theoretically make it more foolproof, let's say. And this is the answer for the last question. Now let's solve a question regarding the margin for the continuous case, and here are the formulas that we're going to need. And here's the thing I'd like to bring your attention to. So in the continuous case, we always like to find general functions, okay? So we're not going to directly find this one, the probability right away. We're first going to find a function that we're going to call the marginal probability distribution function, okay, this one here. So we can later use it to integrate this one right away. So remember, if we would integrate this one, we would have to integrate over the whole region of the variable that is not there, which is y. So we'd have to integrate over the whole region of y, then our desired range of x. But when we find this one, we can directly integrate over the desired range. We don't need to integrate over the whole region of the variable that it's not present, okay? So let's find this one with using this formula there, and it should be like this, where you integrate over the whole region of y, and of course integrating in terms of y, and you're going to find the answer at the end. And for this one also, you can just directly implement the formula, integrating over the whole region of x to find the marginal of y. Now let's solve the probabilities. So for the first probability, we can just integrate this function for the marginal directly here, so we can find the desired probability that we want without the need of going through the whole region of the variable that it's not present in the expression. And for the last one also we can do the exact same thing, just integrate directly towards the desired range without the need of going through the whole the other variable that is not present in the expression also. Yeah, that's basically it. I'm getting tired of repeating myself, and I know you're getting tired too, so sorry. So the mean and variance for marginal distribution. The mean and variance for the marginal distribution, we have a discrete and we have a continuous case. By the way, there is no mean and variance for the joint probability distribution itself. We only have the mean and variance for the marginal distribution. So you can think of them as substitution to the mean of variance for the joint probability distribution. So if you're designing to find any expected values or thing of that sort, actually expected values are very, very, very useful. When you do any stochastic modeling, at least to my limited knowledge regarding stochastic modeling, a lot of the time you're trying to find the expected value to get a good idea about the stochastic model or the stochastic process that you are trying to study. But anyways, let me show you the formulas here. They are very easy. I'm going to just show you the common pattern in here, and I'm going to talk over this one because I have done something quite different in that one. So for this one, it's basically telling you to take the outcome for x. Let's say here, trying to find the expected value for x. Take the outcome for x, multiply it by the marginal probability of x, and do that for all the outcomes that you have. And for y, the same thing, multiply y by the marginal probability for that y, and you're going to find the answer at the end. We're going to solve questions on them, and you're going to see how we can solve them. And for the variance, same exact idea. Just square the outcome before you multiply it by the probability, and at the end, when you finish summing everything, you should subtract the expected value. So here, the expected value of x is going to be subtracted, and here the expected value of y is going to be subtracted. This one, you might have not seen this one. You might have seen a different formula. And in my opinion, this one is easier to remember and easier to understand, to solve with rather, not really to understand, to solve with. So I have substituted this one in place of that one. If you want to use the one that's provided in the book and provided also in your slides, you can totally do that. It's absolutely fine. But I prefer using this one, and these ones are the ones I'm going to use in my explanation. Okay, by the way, you can see that this mu and this expected value, this is basically the same thing. Just don't worry. Just different notation for the expected value. So for the mean and variance for the marginal distribution, for the discrete, let's see the questions. So the expected value of x and the expected value of y, the variance of x and the variance of y, everything is easy. Let's put the formulas there and try to solve using them. So let's find the expected value of x first. This is the formula for it, where we have to multiply x, the outcome, by the probability of that, the marginal probability of that outcome rather. And here we're going to multiply 1 by this marginal. Bear in mind, this table now is extended. Now, since we know how to find the marginal, we assuming that we have found it for all of the outcomes here. So these are the marginal for x, and these are the marginals for y. So when we try to find the expected value, we multiply the outcome by its marginal probability, which is this one here, and we do that for this one also, and we do that for this one, and you should end up with the expected value for x at the end of the day. Should be basic. For b, expected value of y, same idea. You take the outcome for y, you multiply it by its marginal probability, and you do that for all of the values for y here, and you should end up with the answer at the end. For the variance, it's same. You just square the outcome before you multiply it by the marginal probability, and at the end, when you do it for all of the outcomes that you have, you subtract this mean squared. Hopefully it is clear, and same goes for y. Just implement the formula right away. Okay, this is the answer for this one. This is for y, and yep, that's it. That's it for the discrete case, of course. Now for the continuous, we're gonna have the formulas here, and we're just gonna implement them right away. So for the expected value for x, you can implement the formula right away there, where you multiply this function by x, and you integrate over the whole region of x and whole region of y, which should yield the answer here at the end. I believe because this chapter is mostly solving and using formulas, I don't think much explanation is needed. I think just showing the expression here, or showing the thing here is enough to explain the whole idea. Maybe a few talking points would be important to highlight, but for the most part, I think if you have the slides, you're going to be able to solve this chapter very easily. So for the expected value of y, here is the formula, and just multiply a y with this probability joint probability density function, you should end up with the expected value of y at the end. For the variance, same thing, same exact idea. Instead of multiplying by x here, you multiply by x square, and then at the end, after you finish integrating everything and you finish, خلاص, you subtract it by this expected value squared. That's basically it. Same goes for y also. Yep, very nice. Conditional probability distribution. So for the conditional probability distribution, we have two formulas since we are dealing with two random variables. If we had more, we would have more. But the basic principle behind it is very easy, and it's actually exactly the same as the one in chapter 2. So if you have, let's say, y given x, you would have to have the intersection between x and y, or y and x, and divide it this time by the given probability. In this case, it's x, so you divide by the marginal of that x. We're going to solve questions on it. It's very easy, and here is the case for when y is given. So this is basically it. Find the intersection between them and then divide it by the marginal of the given one. Okay, yep. So here's the question, and here are the questions rather, and this is the formula there, and let's solve these parts of the question. So the probability of y equals to, given that x equals to, let's implement the formula right away. So in our case, let's find the joint probability between y equals to and x equals to, should be this one here, and then divided by the marginal of x equals to, which should be this one here. So it should be 0.03 divided by 0.25, and this should be the answer or the probability that you're looking for at the end. I think by solving this one, you can solve the rest. So if you want to solve the rest, you can pause the video, because I'm going to solve them in 3, 2, 1. So for this one, basically implement the same formula, find the joint probability between them both, and divide it by the marginal of the given one, which is y in our case. So it's going to look something like this. For the last one, same exact boring procedure. So find the margin, find the joint between them, divided by the margin of the given one, and you should end up with the answer at the end of the day. Yep. Now let's solve the continuous case. Determine the value of c such that the function, same question, and here are the parts of the question. As I have mentioned, for the continuous case, we like to have general functions so we can utilize them directly in implementation here, without doing much tweaking or doing so many integrals and things of that sort. We just have to have a general function that will account for these cases that we are trying to find the probabilities for. So for the case where we have x as the given probability in here, we can just take this function here, the joint probability function, this one, we take it here and divide by the marginal, which we already have found in the previous in the previous slides. And this should give you the general function for the conditional probability of y given x. Okay, we're going to use it in question C, so don't worry about it. We're going to see how to solve a question using it. So for this one, we're going to do the exact same, with the only difference that y is given in this case. So we're going to divide by the marginal of y, and this we're going to find, with this we're going to find the answer. Now let's solve the question, the probabilities. So probability of y less than 2, given that x equals 1. So just integrate this one, since we are dealing with the joint probability or the conditional probability. You want to the conditional distribution function, integrate it over the desired region, which is, I denoted it as b, which is from 0 to 2 in this case, and you're going to find the answer at the end. Here's the thing. Sometimes you might not get only 2y in this case. Maybe you would have 2yx, okay? So in this case, when you come and implement it here, you're going to have an x remaining. So this x would have a value that equals 1. So if you have an x in here, just substitute it with 1, since the given one here is that x should equal 1 in our case. Okay, so let's solve the last one. Probability of x greater than 1. This is b, and this desired region, we're going to integrate this function here, and this is basically the probability that we are trying to find. The mean and variance, also the conditional probability distribution have a mean and variance, and here are the formulas for them. So yeah, we're going to implement them right away. Here is the question for the discrete case. So the expected value of x, given that y equals 1. Here is the way that I'm going to solve it. You can solve it using the mathematical expressions or the formulas in here, which is the one that I prefer. But I'm going to show you how you can solve it directly from the table. So let's say the one given here is y equals 1. So let me put a small rectangle here around y equals 1. Now what I'm going to do is I'm going to find the probabilities or the joint probabilities between all x's and y equals 1. So it should look something like this. And I'm going to multiply them by, of course, the outcome. But at the end, I'm going to divide them by the marginal probability distribution for 1, which is 0.28. I'm going to show it here. It's better than me explaining it. And this should be the answer for the question at the end. So yeah, that's basically it. So what we did is that we took the values here, these values, okay, since we took these values, and then we multiplied each one of them with the outcome, like we are finding an expected value, and then at the end, we took the margin and we divided it by it here, okay? So that's basically it. Let's go to the expected value of y, given that x equals 1. We're gonna draw the rectangle around the given value, which is x equals 1 here. We're gonna find the probabilities here. These probabilities are the ones that we are interested in. We're gonna multiply each probability by the outcome we have, which should look something like this. And then we're gonna divide it eventually by the marginal of the given one, which is 0.2. So this is basically it. Let's move to the variance. Almost same exact procedure. We, instead of multiplying by the outcome itself, we multiply by the squared outcome, and we should end up with an answer. So it's like this one. It's basically like this one, but instead of having 1, 2, and 3, you should have 1, 4, and 9, which you're gonna see right there. So it doesn't matter if you have one big one big denominator or separate denominators. I'm just doing separate denominators because sometimes the slides are not enough. So for the last one, also the same exact procedure. Yeah, go along with it. Yep. Now for the continuous case. So for the continuous case, it's a little bit better. So we're just gonna implement these formulas, but we need fx given y and fy given x, which we have already found in the previous few slides. So we're gonna just use them to find this value, and here it just tells you to integrate this function. If you want to find the expected value of x given y equals 1, you take this function here and you integrate it over the whole region of x, and you multiply it by itself, or you multiply it by x first, then you take it over the whole region of x. It's shown here better than me explaining it, and this is going to be the expected value at the end. Same goes for y also, and we're gonna do this. We're gonna implement the formula. It's gonna give also. It's gonna yield the same answer also, but instead of integrating in terms of x, here we're integrating it in terms of y. And for the variance, instead of multiplying by x directly, we're gonna multiply by x squared, and then at the end of the day, we're gonna subtract the mean squared, and we're gonna have the variance. And for the last case, also the same exact thing. Instead of multiplying by y, we multiply by y squared and then subtract the mean squared. I'm getting tired of repeating myself. Seriously. Independence. Okay, let's talk about independence a little bit. So here are the 4 conditions or four cases that where you can make sure that your variables x and y are independent. So if either one of these let's say formulas here is or either one of these statements here is true, then you have independence. But if any one of them is incorrect, or at least one of them, or of course, if you get this one incorrect, then the rest are gonna naturally be incorrect also. So, you know, it's either you prove one of them right or you prove one of them wrong, and this is gonna be sufficient enough to tell that you have either independence or not. If they are true, then there is independence. If they are not true, then you don't have independence. But you have to do it for all values of x and y, so all possible combinations of x and y. But if you have one that it's not one combination of x and y that does not satisfy these conditions, you can stop and you can basically say that okay, they have dependence between them, or they don't have independence. So yeah, more than 2 random variables. So here are the generalization for the more than 2 random variables. So if you understand these, you can utilize them in your solution or in solving your models, let's say. And yeah, that's basically it. Now we're going to be solving inclusive problems for joint probability distributions. These are examples from the book that should encapsulate or cover most of the concepts that we have been dealing with, so you can get some good practice along the way, and if you didn't understand something previously, you can see it now. So the question we have is question 5.3 from the electronic version of the book, rather. Show that the following function satisfies the probability of the properties of joint probability density function. Anyways, we're going to ignore that. We're going to just go straight up to the parts of the questions that we have. So the first part of the question says, the probability of x less than 0.5, capital Y less than 1.5. So what is less than 0.5? So here is, if we can look at the x towards the x, we can see that minus 0.5 and minus 1 is less than 0.5. So these ones are included with us. If we go to the y, we can see that what's less than 1.5 is 1, along with minus 1 and along with minus 2. So these are included and these three are included. So the overlap, or you can say the intersection between them, is only these two here. So you would have to only sum these two probabilities here. Yep. Next one, probability of x less than 0.5. Okay, so less than 0.5, so it should be this one and this one. So it should be this one and this one, right? Not necessarily. Take into consideration that you have to include the whole range of y along the way. So if you include the whole range of y, still going to be the same answer. So yeah, so for this case, it's still the same answer. So probability of y less than 1.5. So probability of y less than 0.5 is going to include the whole range of x. So all of this is included along with us. So the one that dictates the probabilities that we take is the desired range of y. So it's going to be 1, minus 1, and 2. So add these three probabilities here, and you're going to end up with the answer at the end. Last one, x greater than 0.25 and y is less than 4.5. So what's greater than minus 0.25 is going to be 0.5 and 1 for the case of x, and for y, what's less than 4.5 is basically the entirety of y. So if we would like to draw the lines and make it visual, so it's going to look something like this. We have the overlap in here. So these are the two probabilities that we actually trying to find. Hopefully it is simple. This is the answer. Move on. Okay, now we're going to find the marginal probability distribution of x and the marginal probability distribution of y. Here is a thing though, since we are dealing with a table or dealing with a discrete case represented in a table, we are not going to have a function rather. See, we're not going to have a function like we have it in the continuous case. The marginal is going to be expressed in terms of a table. As we have seen also in the previous example, it was presented down in the table along the sides of the table. So we can have a table that would represent the general case for the marginal probability distribution of x, because it did not specify here. It didn't say that we want the marginal of x equals minus 1, or it would have been easier. But here he wants the general case, and the general case here would have us find the marginal for all of these things and put them in a table. So it should look something like this. So with this, we have found the marginal. You can use the mathematical expression to see why we have the values here exactly the same as the ones here. But I'll leave it to you. This is the marginal that we are trying to find. The same thing goes for y also. So yeah, you can say that because there is no... because if you can see, for each value of x, there is a unique value of y. For each unique value of x, there is a unique value of y. So you can say there is no common outcome between the random variables here. You can say something like this, because each one of them has a distinct outcome. Each distinct outcome has a distinct outcome corresponding to it in the other variable, and therefore have a distinct probability for itself. You can think of it in this way. You can write the mathematical expression and solve it according to it, and you're going to see that most of these are going to be 0 except for one of them, which is the one that seems most obvious here. Anyways, now we're going to find the expected value of y and x and variances for these two random variables. Here are the formulas, and here is the marginal, because we definitely gonna use it. But you know, since we already know that these are the margin of x minus 1 is the same as this one, you know, you might not need those. You know, if you know what you're doing, you might not need those. So yeah, let's find the expected value of x. So the expected value of x would want us to multiply the value of the outcome by the probability, or the marginal probability rather. We can do it there, since we already know that this one for sure is the margin. So we can do minus 1 multiplied by 1 over 8, minus 5 by 1 over 4, 0.5 by 1 over 2 and 1 by 1 over 8. Sum everything together and you're going to end up with the expected value of x. Same thing goes for the variance of y, but now we're going to solve for the for the expected value of y, but now we're going to solve for the variance of x. And we're going to have similar procedure, the same procedure we have for the variance. So we're going to square the outcome first. So this minus 1 is going to be 1. Then we're going to multiply it by the probability of that marginal probability of that outcome. Same thing for the 0.5, same thing for the other 0.5 and for the 1. So we finished the x's. Now we're going to do the y. We're going to go to the y. So the expected value of y, same thing. We have the table there. You can do it even by yourself if you want to pause the video and do it. It's just basically the same exact procedure. And you're going to find the answer for it at the end. And for this one also, you're going to find the answer for it at the end. Don't forget to subtract the squared expected value. Are we done? No, we're not. Conditional probability distribution of y given that capital X equals 1. Let's have the functions in here and not necessarily going to need the function. We're going to know already that okay, let's solve it using the function. Actually, I solved it using the function. Let me continue with that. So let's start with the first one. For probability of y equals minus 2, we're dealing with a general case. I forgot to mention this. Still here also we're dealing with the general case because he did not tell us it wants the probability of y, for example, equals 1 given that x equals 1. So if he says it in this manner, it means that it wants a general case and you can express it in terms of a table. This is exactly what I'm going to do. So for this case, probability of y equals minus 2 and x equals 1. We have to first find the conditional probability between, find the intersection of them and then divide it by the marginal. So if we find the intersection between minus 1 and 1, it's going to be minus 1, between minus 2 and 1. So minus 2 and 1, there is nothing between them. There is absolutely nothing between them. There's no common thing between them. So this should be 0. So without even finding the marginal, you should know that it should end up 0 at the end of the way. So you can do that for also y equals minus 1, x equals 1. This is y. Hold on. Oh yeah. For y equals minus 1, this is equals 1. There is nothing between them. Like if they were like this, then they have a probability. If they are like this, there is no probability between them. This equals 0. So we already know that this one equals 0 also, and this one would also equal 0, y1 and x1. But for the last one, y equals 2 and x equals 1, we actually have a probability for this, and with this we're going to divide it by the marginal of x that we have already from here, which should equal 1. So 1 over 8 divided by 1 over 8, this equals 1, and this is the table for the conditional probability probability distribution, conditional probability distribution of y. Here I think this should be a y. I think this one should, yes, this one should be a y. This small x here should be a y. I apologize. I'm going to fix it in the slides. So yeah, let's continue. Conditional probability distribution for x given that y. Now the y is the given. We're going to do this exact same procedure. If you want to pause the video and do it by yourself, you're more than welcome. So yeah, we're going to do the exact same procedure. For x, we're going to find first of all the joint between them, then we're going to divide it by the margin. So if we want to find the joint between x equals minus 1 and y equals 1, so we're going to go here. So x equals minus 1 and y equals 1. So they are here. There is no probability between them. I know this one already is 0, and this one also should be 0. It's minus 1 and 1. 0.5 and 1 is the one that has a probability. So this one is going to be 1, and the last one is going to be 0. Looks very trivial. And this is the table for the conditional probability distribution of capital X given that y equals 1. Makes sense. Actually, it makes so much sense. If y equals 1, then you know for sure that x should equal 0.5. You don't need all of this to be done, but you know, just to get you using your hands and solving. Now we want to find the expected value of x given that y equals 1. Let's put the formula that we're gonna need up there and we're gonna use it. So this basically translates to this, and now we have the table for the conditional probability distribution for x given that y equals 1. What we're going to do basically is we're going to implement this formula right away. And this formula says that you have to multiply the x, the outcome, by the conditional probability, which is all of these ones that we have found here. So multiply this by this, this by this, this by this, and so on. You're going to find the probability at the end of the day. Or rather, not the probability, the expected value. It's not a probability, it's the expected value. And it also makes sense. Show that the following function, okay, it's the same question, but now we have to find the independence between capital X and capital Y. So how do we find the independence? We have all these three formulas. We have to make sure that either one of them is true, so we can say that they are independent. If you prove that one of them is true, it's enough. However, you have to prove them for all X and Y. But if one of the X and Y does not match these statements here, if one of them, at least one of the X and Y's, not one of the statements, one of the X and Y's, we're gonna see the case. We're gonna see the case right now. Does not match the what is it called? The statement, then you know for sure they are independent. They are not independent. So we're gonna see it right here. So are X and Y independent? So I want to choose the first one to show that, and I picked these two arbitrary points, the first 2 points. After I finish from them, I'm gonna move to the next 2 points. After I finish from them, I'm gonna move to the next these, and I'm gonna move to these, and to make sure that it's true for all X and Y. But if one of these is not true, then I can stop and I can say they are not independent, or I can say they are dependent. So let's see, is the joint equal to the is the joint probability distribution of them equal to the multiplication of the marginals? Let's see. So here are the marginals that we're gonna use, and here is gonna be the statement that we are gonna make sure whether it equals or not, and obviously it's not equal. So in this case, we know that X and Y are not independent because there is one, for at least one X and Y, this statement did not hold true. Okay, you can choose either one of these if you feel they are simpler or easier, but I chose the first one. So this is, write this in your exam. If you don't write it, maybe you would not get the mark for it, obviously. If you just do this, you're not gonna get the mark. At least that's what I think. Now let's continue. We're gonna solve still inclusive problems, but now we're gonna be dealing with the continuous case. Let's see the question that we have to solve. Determine the following, determine the value of C that makes the function, this function here, a joint probability density function over the range of X and the range of Y. And as we can see here, the range of Y has X in it. So the range of this variable has another variable in it, which is troublesome to us. I don't know if I mentioned this at the beginning or not, maybe because of how many shots I retook because my phone keeps dying. Maybe I didn't mention it. I mentioned it at one time and I didn't mention it at the other, but if you have a variable in the domain or in the range of the other variable, then you might want to do some graphical solution. You want to solve these integrals by first drawing them, then knowing which region you should integrate, and maybe you would have several double integrals that you have to add together. I did not cover this integration part in my slides. There is a guy in the System Engineering Club who explains it quite well. I'm gonna put his video in the description. So yeah. We might need to do some graphical solution. And let me give you a disclaimer, or let me tell you something. If you're summing or if you're integrating over the entire region of X or the entire region of Y, I don't believe you're going to face this problem. Rather, when we solve for expected value or for the variance, we don't face this problem. We don't need to, or also when we are solving for the marginal, also I think for the marginal, we don't need to do all of these graphical solution type of stuff. But when you're trying to find exact probabilities like the ones we're gonna see in the next slide, you might want to do some graphical solutions. Okay, so first of all, let's find the value for C, as we always should do. And I think the procedure is already known to us. We should integrate over the whole region of X, whole region of Y, and equate the function to 1, and we should end up with the value of C at the end. Bear in mind, the arrangement of the integrals matters now, because if you have the wrong arrangement, you might have hanging x's, or you have a hanging variable at the end that has no solution, or it's not it's not covered by the integral, or wasn't solved by the integral. So you might want to take into consideration, if one arrangement of the integrals didn't work, you might want to do the other one. Okay, hopefully it is clear. This is the value for C. Now we're going to substitute it in there. Yep, now this is the new joint probability distribution function. Now let's solve these questions. Okay, these are the type of questions that I mean when I say that you might want to do some graphical solution. So for these questions, you might want to do a graphical solution, and I have solved some of them actually, and I got the correct answer, but for this one, okay, for some reason, well, I know the reason. I drew it, and I know the reason why this is the case. But for this one, you should draw it. You should do a graphical solution for it so you can find it. So I'm gonna portray the answers here for you. I'm gonna show you how I was able to solve them. Except for this one, I'm gonna refer you to the video for it so you can see. And maybe you want to rather solve all these questions using the graphical method that was presented in that video. If we had, instead of x and x plus 2 here, if we had y to have two constants, maybe from 2 to 3 or from 1 to 5 or something like this, we won't need to do any of this, but because it has a variable in the range of it, we are in so much trouble. So let me show you the answers for these questions. And these are the answers. And this one is the special case, refer to this video. And the last one also solved with not much trouble. At least that's what I think. Yeah, let's continue. Marginal probability distribution of x. Well, with regard to the marginal distribution, I don't think we need to worry regarding graphical solution. You want to make sure with your instructor. But yeah, this is my observation. I have seen that when I solve marginal distribution functions and I solve for the expected value, I don't face this problem. I think it has something to do with independence and things like this. I don't really know. But anyways, let's solve for the marginal distribution function. Let's have the formula. Here is the formula, and just implement the formula. It's going to integrate over the whole range of y, and at the end you're going to find this function here at the end. For the expected value, you can just implement the formula here and multiply this by x and integrate over the whole region. Take into consideration that you might want to have a certain arrangement of the integrals dy dx or dx dy, so you don't get left with hanging variables at the end. Yep. Conditional probability distribution function. We're going to implement formulas right away. So this is the formula. We're going to have the joint probability distribution divided by the margin, which we have already just found a slide ago. So divide them by each other and you're going to find the answer for your question. Yep. The expected value is, it has a formula by itself. Where's the formula for it? Okay. Oh, here's the thing. Oh, yeah. Here's the thing. When we do that, we know that x is equals 1 for sure. Okay? X indeed equals 1 for sure. So when we go to the range, we can substitute the range with 1 here. So at the end, we can end up with the whole domain or the new range of y to be from 1 to 3. See? So this is how we obtain the new range or the specified range for y in this case. So to solve the expected value here, you have to integrate over expected value for y. You have to integrate over the whole region of y. So the new region of y is going to be from 1 to 3 instead of writing from x up to x plus 2, because we already know the value for x, which is x equals 1. Hopefully it is clear. Okay, this is the answer. Covariance and correlation. Okay, finally some conceptual points to be explained. So the covariance and the correlation are two brothers actually. The covariance is older than the correlation. And there is similarities between them and there are distinctions between them. Both of them try to find a relationship between the two variables in a data set or in a function or in something of that sort. So if you want to find the relationship, maybe if you increase x, y should increase, or x, if you increase x, y should decrease, and things of this sort. These two guys are your friends in here. But there is a clear distinction between them. The correlation, if I would define it, I would say it is a scaled covariance. Yes, the correlation is a scaled covariance. We know that the correlation goes from -1 up to 1, but the covariance go actually from -infinity up to infinity. So let's say that we have two data sets, okay? Two data sets. They are different from each other, entirely different from each other. And you are trying to find the covariance for this one and for this one, so you would know what's the relationship between x and y. So for this data set, you can get the covariance to equal 100. And for this one also, you can find it to be equal 100. But for this data set, 100 would mean strong positive correlation. But for this one, it will mean there is nearly no correlation between, there is nearly no or negligible correlation between x and y. So that's why we use the correlation. Did I say correlation? Oh yeah, correlation, it's still. But for the correlation, if you get here 0.5, or let's say if you get 1, let's say as a correlation for the data set, the first data set, and 0.1 for the second one, you know for sure that both of them have a strong relationship between the variables in there. So this is basically it. The correlation solves the problem that we face in the covariance, that it's not really scaled, so it scales it down or scales it in a way that we can really make interpretations using the numbers. So let's see a little bit more regarding the covariance. It's denoted with sigma xy, or covariance of x and y, and it has a range going from -infinity up to infinity, and it has this formula. So first of all, you have to find the expected value of x and y, and then subtract that from the mean of x and the mean of y. Okay, so the expected value of x and y is found in this way, because it's not shown in the book. I had to look for it in the internet, and this is the formula for it. And this is the expected value of x and y. This for the discrete case, which is shown in the book, or in the slides also. I got it from the book though. Now with the correlation, we know that the correlation is denoted by rho of xy, and the range goes from -1 up to 1, where -1 denotes a strong negative correlation and 1 denotes strong positive correlation. This is the formula for the correlation, where you have the covariance on top divided by the standard deviation for each one, for each x and each y. And here is a nice picture that shows you the meaning of the values for the correlation. So for example, if you have something from -0.8 up to -0.6, you can say that there is a strong negative correlation between these two variables. Okay, hopefully this is clear. Now let's solve questions. Oh, before we have some conceptual points. If the covariance equals 0, then the correlation equals 0. So if either one of them equals 0, then you know the other one equals 0. We have said that it's different from each data set. So maybe in this data set you can get 100, and 100 means strong negative correlation, strong positive correlation, and the other data set you get the covariance to also equal 100, but there is no correlation whatsoever. But if it equals 0, then you know for sure that there is nearly no correlation whatsoever between them. Okay, so yeah, that's basically it. There is another point that says that all independent variables have 0 correlation. Okay, 0 correlation. However, not all correlations are independent. 0 correlations are independent. So what do I mean by this? If you have independence, then you know for sure that there is 0 correlation. But let's say that you calculated the correlation first, and then you got it to be 0. Can you conclude that there is no dependent, or there is independence between the two variables? No. You have to calculate for the independence, then you can make sure that make sure of that rather. So if you would like to make it into a logical proposition, it would look like this. It's an implication where independence implies 0 correlation. You can draw the truth table if you're into that, but yeah, hopefully it's clear. It took me a while. I read it a few times until I understood it. When I heard my instructor or my doctor say it, I didn't really understand from the first time. It took me a few times until I understood it myself. Now let's solve questions for these guys. So the first question says, we want to find sigma xy, which is what? Which is the covariance. So let's have the formula for the covariance right there. So we have to find expected value of xy, and the expected value of x, and the expected value of y. Let's start with the expected value of x, and the way we found it is just basically by multiplying each outcome by its probability, and that's basically the way. By the way, these are, you can do it in terms of marginal probabilities, but for this table it is easier to do it just in this way directly. So you can just find the expected value at the end. And the same goes for the y also. Just multiply 3 by 1/8, 4 by 1/4, 5 by 1/2, and 6 by 1/8, and you get this at the end of the day. For the expected value of x and y, you multiply x, and then you multiply it by y, and the product you multiply it by the probability. So it should look like this. This is how you find expected of x and y. With this, we have everything we need, and we can find the covariance easily. The covariance is 0.7031. Now moving forward to the next part of the question, where we need to find the correlation. So rho xy, let's put the formula there because we definitely gonna need it. And the formula says that we need to find the covariance, and we divide by the standard deviation of x and the standard deviation of y. So what we can do in this case is we can find the variance for x first. So the way we found it is almost like the same as the way we found the expected value for x, but instead of multiplying by the outcome by itself, we multiply it by the outcome squared, and with this we find and at the end, of course, subtract the squared of the mean, and you find the answer for it at the end. Same thing goes for y, and the covariance, we already have found that, so good for us. With this, we have everything we need to find the correlation, and the correlation is 0.885, which means that there is strong, actually very strong, positive correlation between variable x and variable y. As we can see, if you increase this one, the other increases also, so it just makes sense. Okay, moving to the next one. Now we are talking about the continuous case. So the question says determine the value for C and the covariance and the correlation for the joint probability density function. This one, it looks very similar to the one we had at the beginning, but there is a difference that the range is different here. So we have the range to be this one. As we can see, the range has a what is it called? A variable in it, but it shouldn't be much of a problem, at least not to my experiments. I've seen that it doesn't propose much problems. If you've seen something that's otherwise, please tell me so I can fix the slides at least. So yeah. The way to do it, okay, we are definitely first of all trying to solve C. We have solved C about 3 times now, so the procedure is quite the same. Integrate over the whole region, equate everything to 1, and you should end up with the value for C at the end. So moving forward, we're gonna find B, the covariance of x and y for this question. Let's have the formulas that we're gonna need. So as we can see, for the covariance, we need the expected value of x and y and the expected value of x and the expected value of y, and here are the formulas for each one of them. So let's start by finding expected value for x, then finding expected value of y, then expected value of x, y, and at the end bring everything together and find the covariance for that for this probability distribution function. Moving to the next part of the question, we're trying to find the correlation of x and y. So to find the correlation, we need these functions or these formulas there. As we can see, the correlation would require you to find the covariance, which we have already found in the previous step, and also to find the variance for x and the variance for y. So finding the variance of x like this, implementing that formula, multiplying this probability density function by x squared, and then integrating over the whole region of x and y, taking into consideration the order of integration also, because you don't want to be left with hanging variables, and do the same exact thing to y, with the exception that you're going to be multiplying with y square. Here the covariance, we already know it, and the correlation is this value after you substitute everything. Of course, these things are variances, so put them all under the square root to make them all standard deviations, and you're going to find the answer at the end. Now let's talk about the multinomial distribution. The multinomial distribution is like the older brother for the binomial distribution. In the binomial distribution, it was a binary. That's where the binomial come from. The bi here is come from the binary. There is only 2 outcomes that we have. Here we have multiple outcomes. So instead of only having success or not success, or defective or not defective, you can have maybe defective, partially defective, or good, something like this. So you can have multiple multiple items in your list, and they would be considered, and they would be modeled using a multinomial. Of course, if all trials are independent, maybe if you're pulling something, you pull it with replacement or something of this sort. I think I forgot to mention that when I was explaining the binomial distribution, but I'm going to say it now. If you're going to pull something out of the cube, out of a box maybe, or out of a bag, you'd have to replace it back in for it to be considered a binomial. Otherwise, it would be considered as a geometric distribution. Okay, so let's see the formula, the huge formula for the multinomial, which is a huge generalization here for the binomial distribution, where n is still the number of trials, but p, or let's say start with k, which is the variable we have in here, is the number of success for the kth item. So maybe you said we have more than 2 items, so maybe there is item 1, item 2, or item 3, or you can say item defective, partially defective, or non-defective. K would denote how many successes of that item you want, and P would denote the probability of success of that said item. Okay, while N is the number of trials naturally, and we have a mean and variance. Here is a difference in notation that I have noticed. Here we have K and here we have I. I think if you replace well, K, I think it's to denote the largest outcome, but here it's almost the same thing. So if you want the expected value for, let's say, the one of the items, let's call it item 1. So you'd have the expected value of x1 multiplied by the probability of that that said item, which is going to be P1 in this case. Same thing goes for the variance also. I don't know why they have it K in here and have it I in there. Maybe K is the biggest number here, maybe something like this. I have no idea. So the question says, test results from an electronic circuit board indicates that 50% of board failures caused by assembly defects. So this is the first type of defect we have. 30% by electrical component. Okay, so this is the second type of defect we have. And 20% by mechanical defects. Okay, good. Suppose that 10 boards fail independently. Good, we know that the failures are independent. Let the random variable capital X, capital Y, and capital Z denote the number of assembly. So capital Z is the assembly failure, and capital Y is the electrical failure, and capital Z is the mechanical failure among 10 boards. Very good. Let's put down the parameters that we have, and as we can see here, for X, it's the assembly failure, so the probability of assembly failure is 50%, as it's written up here. And for the electrical one, it's 30%, and for the mechanical one, it's 20%. And we have written them all here because we're definitely going to use them, and the number of trials we have are 10. Now let's see the parts of the question. The first part says, find the probability of capital X equals 5, capital Y equals 3, and capital Z equals 2. You have everything you need. You can solve it right away just by implementing the formula right there. There is no tricks about it. Maybe if you give it a look, maybe you're able to produce the solution, and this is how you're gonna solve it if you want to solve it, just by implementing that formula there right away. You have this n factorial, and we have the number of desired success, the x's, the number of success for X here, the number of success for Y, and the number of success for Z, all factorial, and then we multiply the probabilities by the number of trials, or the number of successes that we have, rather, not the number of trials, the number of successes that we want for each outcome. If you read the formula, you might be able to hint it out yourself, and that's basically it. So this is the answer here at the end. The probability of X equals 8. Okay, what is this? This is the marginal distribution. This is a marginal expression here, actually. And the beautiful thing about the multinomial, that the marginal of the multinomial is what? It's the binomial. So this question, we can solve it as a binomial question that easily. So a binomial of n, 10 trials, the same n, but the probability of success is going to be the probability of success for the variable that we have naturally, which is capital X, and we can see the probability of success of capital X is 0.5. And with this, we can just solve it as a binomial question that easily. Next one, probability of capital X equals 8, given that Y equals 1. Okay, so with this, we can just basically solve it as if we are solving a conditional probability, where we have to find the intersection between these two events first, or the joint probability of them, then divide it by the given one. But pay attention to something. We want to have 8 successes of X, and we already have 1 success of Y. But bear in mind, we have 10 trials, n equals 10. If you sum these two, you're going to end up with how much? You're going to end up with 9. So there is 1 additional success that you have to account for here, that's why we added Z equals 1 in this case. So when we sum everything in here, we should end up with 10 at the end, and then you divide it by the given probability, or the given event. And this event also could be modeled using a binomial. This is how I solved it, also as if it was a binomial question. The expression in the denominator, and this is basically the probability that you are looking for. The probability of capital X greater than or equal 8, given that y equals 1. Same kind of idea, but now you have to solve these two expressions. So for this expression, we have already solved it if you recall. And this one, you would solve it in the same way, and you should get this answer at the end. For the last one, there is not much about it. Just find the intersection between them all. They are already sum up to 10. 7 plus 1 plus 2, they are already sum up to 10, so you don't need to add anything here. And also when you're trying to solve this one, 9 and 1 already add up to 10, so you don't need to add an additional z in there or additional event to account for all of the trials that you have. Okay, so this is basically it. This is the answer for the multinomial question at the end. Now let's talk about the bivariate normal. So the bivariate normal is like having two normal distribution and combining them together into a higher dimension. So we don't need to go too much in details, and we don't even need to know what is this joint probability density function is all about. We're gonna solve it like we used to solve the normal distribution with few tricks that we can use to solve the bivariate. So here are the parameters, all the parameters in addition to the variables that we have: correlation coefficient, variance of x, mean of x, and so on. Actually, the standard deviation of x, not the variance. If it was squared, it would have been the variance. I'll correct it. So, and we have the conditional of the bivariate also. So if we have any questions regarding the conditional of the bivariate, we can use these means and variances so we can standardize eventually and find the answers for them all. We're going to see all of that. Don't worry about it. So here is a special thing about the bivariate normal though. In the previous case, when we used to have independence, then we know that we had zero correlation, right? But if we only have zero correlation and we don't know whether it's independent or not, we cannot conclude that it's independent, but just by knowing the zero correlation. But for the bivariate, it's not the case. So if you have independence, then you know that you have zero correlation. And in turn, if you have zero correlation, then you know for sure that you have independence. So this is a special case for the bivariate. The relationship, if you're into this logical proposition type of stuff, independence and zero correlation for the bivariate normal distribution has if and only if, I don't know, relationship between them or something like this. Okay? So, since the bivariate normal is a normal distribution, naturally, we always like to standardize the normal because it's way easier to standardize it and solving it using the tables that we have, because it's difficult to integrate the normal distribution, and you can only find empirical solutions for it. At least that's what I have heard. So using the tables is standardizing, and then using the table is well, ironically, the normal thing that we like to do. Here. So here are the cases for the case for x and the case for y, normal x and y, not normal in meaning normal. Well, x, yeah, they're normal, also normally distributed, and also the conditional of these x and y. Okay, let's solve a question. I guess yes, this is the question. Suppose that capital X and Y have a bivariate normal distribution of these I don't know, these parameters here. So let's see. The first question says the probability of capital X being between this value and this value. What we do, well, we know that this is a joint probability distribution, but everything with regard to the bivariate is kind of special, so we don't need to include the other random variable into the mix. So all we can do is just straightforward standardize and solve right away like we are solving a normal distribution. And the same thing goes for the other question here. We just standardize, but this time, I forgot to mention, you're going to standardize the x with the mean of the x and the standard deviation of the x. Here you're going to standardize it with the mean of the y and the standard deviation of the y, and these are given here already in the question. Hopefully it is clear. Yeah, this is basically it. You're going to solve the question and you're going to get the same answer also. Let's move. Same question. But now we're going to use the property of independence. I think I've spoiled it by doing this, but anyways. So this question now, this part of the question have both x and y joint. Okay, so both of them are in the same expression, so they are joint. How to solve them though? Do we just standardize and go about our way? Well, it's not directly in this way. But since we know that if we have zero correlation, then we have independence, then we know that we can separate these joint probability distributions into two marginal distributions and multiply them by each other. What do I mean by this? I mean something like this. So we took the x, we put it aside, and then we took the y, we put it aside, multiplying both of these together, and I forgot to make this a y. That's a really big mistake. But I'm not gonna do the shot. I'm gonna fix it in the slides though, sorry. So with this now we can standardize everything. Bear in mind this is a y. So when we standardize everything, everything turns into a z. That's amazing. So yeah, basically find this answer here at the end. So yeah, basically that's it. Another question, here's another question. In an acid-base titration, a base or acid is gradually added to the other until they have completely neutralized each other. Let capital X and capital Y denote the millimeters of acid and base needed for equivalence, respectively. Assume that capital X and capital Y have bivariate normal distributions. Okay, I don't understand what's being said, but I can solve the question. So the question says the covariance between capital X and capital Y, it's the one that they want to find. So let's have the formula for, well, ironically, you would put the formula for the covariance, but we are not going to be able to solve using the formula for the covariance. We're going to be able to solve using the formula for the correlation. The idea is that we already know the value for the correlation here, and also we know the value for sigma x and sigma y, and the one that we want to find is the covariance, the one up there. So just basically manipulate this formula a little bit and you're going to find the answer for your question at the end, which should equal 6 at the end. Okay, next part, probability of capital X less than 116 given that y equals 102, and since this is a given probability, we have to standardize it given the standardized we have to standardize it given the conditional mean and the conditional variance. So here is the formula for it, or this is the way you can standardize it, but we don't have this one or this one. But recall in the first slide we have the formulas for these, so we're gonna put them here because we're gonna use them, and just use them because you have everything in here. You have the mean, you have the mean of x, the standard deviation of x, the standard deviation of y, and so everything. You have everything that you need in here. So with this, just find the answer at the end for the mean of x given y, and the variance for x given y also, and use it to standardize. Bear in mind this was 16, we made it 4 because we took the standard deviation. We don't want the variance when we standardize, and with this we can solve it like it is a normal, standardized normal distribution using the table. Now we're going to talk about the linear functions of random variables. And what I mean by linear function of random variables is a function like this, where we have capital Y equals the sum of some random variables by itself. So you might say, well, weren't we dealing with functions of random variables also, like the binomial distribution, like the exponential? I will tell you, not really. The random variable was in these functions just to map out the outcomes and to assign a real number to them so we can access them when we are solving for their probabilities. But now we have the whole random variable inside of our function. So this is going to be extremely useful in even real life situations. And understanding this part of the chapter is crucial to understand a big part of chapter 7. So you might want to pay attention a little bit, especially when I talk about the properties of these linear functions of random variables. So here we have, by the way, naturally, if these are random variables, capital Y is also a random variable by itself. So I think it goes without saying. So here, the capital letters are the random variables, as we have mentioned about 3 times now, and the C's are the constants. So that's just basically it. So the C is any constant, either 1, 2, 3, well, whichever it is. So let's move forward. So finding the mean of these functions of random variables should look something like this, where you can find the expected value of each individual random variable by itself, and the constant that it was multiplied by this random variable could leave the expected value function just as it is, which is extremely helpful and extremely useful. Let me show you something though. There is something people say, which is that the expected value of the sum is equal to the sum of expected value. Here what we have is the sum of expected values. But let me show you what I mean by the expected value of the sum. Let me give a really simple trivial example here. Let's say capital Y, okay, equal to capital X1 plus capital, let's say 3 multiplied by capital X2, just for the sake of it. If I want to find the expected value of this, I can say the expected value of capital Y equals the expected value of X plus X1, capital X1 plus 3 capital X2. And this in turn, let me make this a little bit more apparent, and this in turn should equal the expected value of X1 by itself plus 3, you can bring the 3 outside of the expected value, or let me write it here, the expected value of 3x2, and this 3 can come out, so we can arrive at this final shape for this function, 3 expected value of capital X2. So this is the way you find the expected value of capital Y in this case. So yep, that's it. The idea is very similar to the variance, by the way. It applies to the variance also, but the only exception with the variance is that when the constant leaves the variance function, it becomes squared. So this is something you would like to pay attention to. So yeah. And the variance has actually 2 cases where there is independence and there is no independence. I don't think we're gonna care about this one at all. All that we're gonna care about is the case where we have independence rather. Yes. So let's solve a question based on that. So X and capital Y are independent normal variables with the expected value of X, variance of X, variance of Y, and so on. Let's see what we can do with this. So how do we find the expected value of 2x plus 3? Recall what I have just done on the board. So you can take the expected value of these individual variables by themselves, and you have here the constant, so you can get rid of them by taking them out. And now the expected value of x is here, and the expected value of y is there. So just substitute them in place of the ex and ey, and you basically got the answer at the end. So this is the expected value of this expression. For the variance, you would do something like this. Just basically the same thing, taking the variance, instead of having the sum of variance, the variance of the sum, you have the sum of variances, and then you bring the constant outside squared. And this is basically how you solve this question. Very easy. Now let's move. Okay, now we are finding probabilities for that. So we already assume that it is normally distributed, so we can standardize it. But how can we standardize it? By the mean of this expression and the standard deviation of this expression. Also, we already found the mean and we already found the variance, so all we have to do is just take the square root of the variance and standardize it as it is. We're going to get z2 equals 0 at the end, which is going to equal 0.5 eventually. Same idea with this. If you want to solve it by yourself, you're more than welcome. Here is the answer for it at the end. Okay, hopefully everything's clear. Let's move to the next question. The next question says, making handcrafted pottery generally takes 2 major steps: wheel throwing and firing. These are the 2 steps that it takes to make handcrafted pottery. The time of wheel throwing and the time for firing is normally distributed using a random variable with means of 40 minutes, that's for the wheel throwing, and 60 minutes, that's for the firing. So this is the mean for the wheel throwing, this is the mean for the firing, and standard deviations of these respective steps. So this is for the wheel throwing and this is for the firing. Okay, what do you want from us? What's the probability that a piece of pottery will be finished in 95 minutes? Okay, so a piece of pottery being finished means that it finished both of these steps. Okay, so the time until it finished step 1 and the time until it finishes step 2, these 2 are the time until what? Until a piece of pottery is finished. So we can make a variable and we can call it the time until a piece finishes, and then we can make 2 other random variables, each one for each step. So for the wheel throwing, or for the first step, we can call it capital X1, and for the second step we can call it capital X2, and the sum of them both would denote when the piece, or when rather the pottery, the piece is finished. Okay, so in order to solve this, well rather now, since we have actually a random variable to denote all of this, we know that the expression that we need to solve is this one, the probability of capital Y being less than 95, because it will be finished within 95 minutes, so it's going to be either 95 or less. And we know that this is normally distributed because both random variables are normally distributed, and adding two normally distributed random variables would eventually lead to a normally distributed random variable at the end. So, but we need to know the mean and expected, the mean or the standard deviation for capital Y in order to solve this question. So how can we solve it? Well, we can basically find it using the expected value of the sum and then separate them to find the sum of expected values, and with this would end up with this answer at the end. So recall capital Y with throwing has a mean of 40 minutes and firing has a mean of 60 minutes. So if we add them together, it's going to be 100 at the end. So with the standard, with the variance, it's almost the same idea, and that's basically it. But bear in mind, this is the variance. We need the standard deviation, take the square root and standardize accordingly and find the answer at the end. Hopefully it's clear. Moving to the next question. It's the same idea. The question is the same idea. You can pause the video and solve it by yourself. There is nothing new to it. So yeah, I'm going to show the answer right now. So yeah, basically the same idea, but here's the probability. The next question says that the width of a casing of a door is normally distributed with this mean and this standard deviation, and the width of the door itself is distributed with this mean and this standard deviation. So let's see what they wanted from us. They also told us that they are normally distributed and they are independent. So they want from us to find that what's the probability of the width of the casing minus the width of the door exceeds 1/4 inch. So they literally gave us the function inside of the question. So we know exactly what's the function that we're gonna write. So let me define my random variables. My random variable capital Y to be the difference of these two, the casing minus the width, the width of the casing minus the width of the door, and capital X1 to be the casing width, and capital X2 to be the door width. And I know the equation that I need to write is the one to be subtracted in terms of the other. We know the door is subtracted from the casing because it's written in here. And with this, I can write the probability expression here. And I know already it's normally distributed, so I can solve it like it's a normal distribution, but I need to know the expected value and the standard deviation to standardize it and solve it. So let's find them together. Here is the expected value. The same procedure as we used to do, and just basically this is the expected value that we're going to use. And for the variance, I want you to pay attention to something. Here it became positive. For a good for an obvious, well, might not be very obvious, but if you take the variance of x by itself and variance of x1 and x2 by itself, x2 would be included along with the negative sign. And when you bring the negative sign outside, you can assume it's multiplied by -1. And when you bring -1 outside squared, you're going to end up with 1 at the end. So it's going to be positive between them. It's going to be a plus sign. So if we have everything we need, just pay attention. You have to take the square root because we want the standard deviation. This is going to be the answer at the end for our question. I'm going quickly because my phone is going to die and I don't want to come here again. So the width of the casing, it's the same question. What's the probability that the door does not fit in the casing? Okay, that's a very, very good question. So here in the final equation here, how would the door not fit in the casing? If the door is bigger than the casing. So if the door is bigger than the casing, when we come to this equation, this is the door and this is the casing, and if this is always bigger than the casing, then the value for capital Y will be negative. So this is what we are trying to look for, capital Y being negative. So with this, we have everything we need and we just have to solve it as it is. Okay, now for the last portion, hopefully I finish it before my phone dies. The general function of random variables. We have discrete and we have continuous case. So for the discrete case, this is the function. I'm not going to talk much over it. I'm going to show you how to use it and how to solve the questions using it. And for the continuous also, here is one thing I want to denote. This is called Jacobson something, which is only the differential of this one. So differentiate this one, you're going to get that one. And you should take the absolute value of it. So as it's denoted here. So yeah, let's solve this question. So this question says that this is the function that we have already, and we want to find the probability distribution of it being like this. So y equals x squared. So the first thing I want you to find is u of y. So how to find u of y? This one is in terms of x. I want you to make it in terms of y. How? Just take the square root of both sides, and this is going to be your u of y. This is basically it. Whichever is here, make it in terms of y, and this is going to be your u of y. So with this, plug this u of y, as you can see, in the function. So replace all the x's in here with this one. So eventually you will going to find the answer for this question at the end. Not only this, but also the range. You can find the range by plugging the x inside of here, and you're going to iterate over it multiple times, and eventually you're going to find this range here. So x1 would equal y would equal x squared, so 2. Y would equal 4 in this case if x equals 2. It's very easy. Let's solve another question. The question says, suppose that, okay, probabilities will determine the distribution. So this is a distribution. The first thing I want you to do is what? To make this in terms, instead of it being in terms of x, make it in terms of y. So you're going to end up with something that looks like this. Take this, is going to be your u of y, plug it inside of this function. So when you plug it inside of this function is actually constant. There's no x's in there, so it's going to look the same, but the only thing that's going to change is the range. And how you find the range? 1, plug it in here, is going to be the range. 2, plug it in here, is going to be the range, and so on. So yeah, let's move to the continuous case. So the example for the continuous case, hopefully the phone did not die, is going to be this one. So it's going to do the same exact procedure with only additional steps. So what we're going to do, we want to make this in terms of y first. So we're going to do it like this. And then we're going to take this one and plug it inside of here. But also we want to differentiate it so we can find the Jacobson, the absolute value for the Jacobson. So when we do that, we should bring everything together and we find the answer for this at the end, and you find the range in this exact same way. Okay, the final question of the chapter. This is the function that we have. We want to make it in terms of y instead of it being in terms of x. So what do? We take the exponential of both sides and we end up with this expression here, and this is going to be our u of y, and when we take the derivative, this is going to be the Jacobson, and with this we can just put everything together and eventually arrive at the answer. By the way, the range here is different because I don't know why. So I don't know why the range here is different. Yeah, the range here is different actually because when we plot this one, we're gonna see that it goes from -infinity up to infinity. So I think it's a little bit different for the continuous case. So yeah, you can just look at this one and see what's the range, like you're solving a question in Math 001 or something like this, and gonna be the answer. So I think this is it. Hopefully the phone didn't die. So with this, I think we conclude this chapter. Thank you so much for watching, and that's it.